Hello, my name is Valeria Miguel, and today I will be presenting an experiment on the drag of simple shapes and the calibration of the force balance. In this presentation, I will be discussing the motivation behind the experiment, an introduction to the experiment, as well as the methods used, the results and discussion of the experiment, and the conclusions. A motivation behind this experiment would include the study for the effects of drag that vary with the shape of an object, the velocity flow, and boundary layer type. For this experiment, an investigation was conducted on the effects of drag based on the shape of an object, which was placed in the wind tunnel test section. A comparison between the resulting drag forces and the coefficient of drags for the varying shape configurations were analyzed, and the different shape configurations that were studied for this experiment include a smooth sphere, a sphere with a wire trip, and a streamlined object, as well as cylinders that varied in length. For this experiment, the ATI Nano 17 force balance transducer was used to measure the forces and the moments on the objects that were placed on the wind tunnel. The equipment that was used for this experiment includes the wind tunnel, which is where the objects were placed in the test section. It also included the ATI Nano 17 force transducer, which measured 2 axial forces, 2 normal forces, and it also measured 3 corresponding moments, the roll, yaw, and pitching moment. The pit dot tube, which measured the fluid flow velocity, the cylinder of various lengths, which was used to find the minimum distance from the wall where the 3D effects are negligible, and the data acquisition system, which was used to find the mean flow velocity, and the blunt and streamlined objects were the objects being used to compare the resulting forces, and the system, which included a computer, control board, and lab view system. It recorded the data acquired by the force transducer. The procedures done for this experiment includes the calibration of the force balance, taking pressure data for 3 object configurations, and measuring the wall effects based on the different length cylinders. For the calibration weights were used and placed on the sting balance at different locations. The weights varied as well as the angle of attacks, and the resulting data was then plotted to verify a 5% error or less. Taking pressure data for 3 object configuration included measuring and recording the diameter of the object and attaching it to the force balance. We had to ensure that the angle of the force balance was parallel to the flow direction. In order to understand the coefficient of drag as a function of velocity, we varied the velocity values, which resulted in axial forces. These axial forces were then used to calculate the dynamic pressure, and it was inputted into the coefficient of drag, and in order to calculate the Reynolds number, we used the diameter of the objects. The same procedures were performed for all configurations, which includes a smooth sphere, sphere with a wire trip, and a streamlined object. For the wall effects, we recorded and measured the different lengths of the cylinders as well as the width of the wind tunnel test section. Then we mounted the cylinder onto the sting balance and set the speed to 35 meters per second. And we recorded the drag measurements. We repeated the same steps for each cylinder. This plot shows us that the calibration of the force balance, this verifies the sensor calibration because it allows us to observe the accurate measures of forces from the calculated forces to the measured from the experiment forces. This plot is a comparison of the drag coefficient as a function of Reynolds number for different configurations. You can observe that the drag coefficient decreases as the Reynolds number is increased. When there is a rapid decrease in coefficient, we are able to detect the critical Reynolds number. Also, it is observed that the coefficient of drag for a streamlined object is the lowest from the other configurations. Here we have a table with the three configurations and their coefficient of drag for their critical Reynolds number. The difference in pressure distribution for the upstream and downstream pressure determines the drag on an object. Therefore, for the streamlined object, we observe there is a lower coefficient of drag at a higher critical Reynolds number. When an object experiences a large rise in drag, that is used as an indication for when the object experiences unfavorable pressure gradients which cause the separation of the boundary layer. Here we have observed that the object with the largest coefficient of drag is the sphere with the wire. In this plot, we have the coefficient of drag as a function of the distance for a cylinder and the wind tunnel test section wall. It is observed that as the wind tunnel test section and the cylinder's distance increases, the coefficient of drag decreases. After conducting this experiment, we found that the Reynolds number increase would cause a sudden decrease in the drag coefficient, and that is due to passing the critical Reynolds number. We vary the critical Reynolds number with increasing the flow velocity. For the wall effects, it was observed that as the cylinders were brought closer to the test section, the drag coefficients increased. Additionally, we found that between the three configurations of the objects, the streamlined object resulted in the lowest coefficient of drag, and this could be due to it having a smaller rate of change of thickness in the downstream direction compared to the spheres. The objects with the faster rate of change in thickness have a larger unfavorable pressure gradients and therefore greater pressure drag and drag coefficients. The references used for creating this presentation includes the Technical Memorandum of Experiment Number 2 used for the MAE 102 course. Additionally, the MAE 108 Laboratory Manual was also used. Thank you for listening.